On March 11, 2011, Japan's coastal defenses failed in real time. A tsunami nearly 50 feet high crossed the shoreline in minutes, overtopping seawalls designed for half that height. Entire towns vanished. More than 20,000 people were lost, and 120,000 homes were destroyed. What shocked engineers was not the earthquake itself. It was the scale of miscalculation. The question was no longer if Japan could be hit by a tsunami, but whether it was possible to redesign an entire coastline to survive the next one. The answer would become the largest tsunami wall ever built. Please take a moment to subscribe and like the video. It really helps the channel. Japan lives with danger beneath its feet and beyond its shores. The country sits at the junction of 4 massive tectonic plates, making it one of the most seismically active places on Earth. Every year, more than 500 earthquakes ripple through the islands, most too small to feel, but some violent enough to reshape the seabed. When the ocean floor suddenly lifts or collapses, millions of tons of water are displaced in seconds. That energy has nowhere to go but outward, racing toward the coast as a tsunami that grows in size and power the closer it gets to land. Before 2011, Japan believed it was ready. Coastal seawalls stood guard along vulnerable shorelines, most designed to withstand waves up to 26 feet high. But the tsunami triggered by a magnitude 9.0 earthquake shattered those assumptions. The quake ruptured more than 300 miles of plate boundary, lifting the seabed enough to send walls of water toward land. In some areas, the waves surged to nearly 50 feet, pouring straight over the defenses. Seawalls were overtopped, towns were erased, and the Fukushima nuclear plant spiraled into crisis. The lesson was brutal and clear. It was not the earthquake that destroyed northeastern Japan. It was the tsunami that followed. In the aftermath, Japan made a decision unlike any taken before. Instead of rebuilding the same defenses, the country committed to a nationwide coastal barrier on an unprecedented scale. Nearly 250 miles, or about 400 kilometers, of continuous tsunami wall would be constructed along the Pacific coast. In many areas, the wall would rise 45 to 50 feet above sea level, with foundations sunk as deep as 80 feet into the ground. The goal was not to block every tsunami. That is impossible. The purpose was to slow the waves, break their force, and buy enough time for people to escape. Before the first truck arrived, engineers turned to science. Every detail of the 2011 disaster was dissected and recorded. Wave heights, arrival times, flow speeds, and failure points were fed into simulations and physical models. In laboratories, scaled versions of the coastline were built inside massive wave tanks. Artificial tsunamis were generated again and again, slamming into test walls until they failed. Engineers adjusted heights, slopes, thicknesses, and foundation depths, pushing each design beyond its breaking point. Only after repeated extreme testing did the final specifications emerge, locked in by data rather than hope. The challenge beneath the wall was just as severe as the one above it. Much of the Tōhoku coastline sits on weak, sandy soil that can liquefy during earthquakes. To stabilize it, engineers drove deep concrete and steel piles into the ground, anchoring the wall to solid layers below. They excavated foundation pits up to 25 meters deep, filling them with compacted sand and crushed stone to create a dense, stable base. The wall's foundation spread outward in a wide trapezoidal shape, preventing it from sliding or tipping under massive horizontal forces. Inside the structure, reinforced steel cages were embedded in vast concrete pores, creating a single rigid system capable of resisting both shaking and impact. Construction stretched across 4 prefectures, from Aomori to Iwate, Miyagi, and Fukushima. Many sites had no existing infrastructure, so entire supply networks had to be built first. Access roads were carved into steep terrain. On-site concrete plants were installed to handle the enormous volumes required. Crane platforms and drainage systems allowed work to continue in harsh coastal weather. The wall rose in dozens of connected sections, each one poured, cured, inspected, and then physically linked to the next. Piece by piece, The segments merged into a single continuous barrier tracing the edge of the land. The ocean-facing side of the wall is not smooth. It is designed to fight water before it hits the main structure. Massive concrete blocks, including tetrapods and dolos shapes, sit in front of many sections, disrupting the incoming waves. Stepped and sloped faces force the water upward and outward, while splash reduction ledges absorb energy and reduce impact pressure. By the time the wave reaches the vertical face of the wall, much of its destructive force has already been stripped away. On the landward side, the design shifts from defense to resilience. Drainage systems channel overtopped water away from towns, reducing flood damage even during extreme events. Soil and rock backfill strengthen the structure while restoring usable land. In many areas, the top of the wall doubles as a walkway, inspection road, or local transport route. Railings, ladders, and safety signage are built in, turning a massive piece of infrastructure into something people interact with every day, not just during emergencies. Ports presented a unique challenge. Fishing harbors and shipping channels cannot be sealed off permanently. To solve this, engineers installed massive tsunami gates at critical openings. Some systems use top-down steel gates that drop into place when warnings are issued. Others rely on bottom-up gates that rise from the seabed, lifted by hydraulic systems powerful enough to resist incoming waves. Built from corrosion-resistant steel, these gates allow normal marine traffic to flow freely, while standing ready to close within minutes when danger approaches. The price of this effort exceeded $12 billion. More than 30,000 engineers, scientists, and construction specialists contributed over 5 to 7 years of continuous work. Computer simulations and physical testing now show that the wall can reduce tsunami impact forces by up to 50% in key areas. More importantly, it can provide several critical extra minutes for evacuation, time that could mean the difference between survival and catastrophe for tens of thousands of people. The wall cannot stop every tsunami. No structure can, but it stands as the largest coastal defense system ever built, a final buffer between the ocean and the communities that live beside it. It is a physical reminder of what was lost in 2011 and a promise that the same tragedy should never be repeated in the same way. From towering tsunami walls to underwater tunnels and earthquake-resistant cities, Japan's megaprojects reflect a national philosophy shaped by disaster. Precision engineering, long-term thinking, and resilience are not luxuries here. They are necessities. When the waves return, Japan intends to be ready. Thanks for watching Unthinkable Build. We'll see you in the next one.